So, welcome to the post-midterm session for our course. So far, we've divided our course into 4 parts and we've done 2. So, we've already looked at some fundamental concepts in which we looked at how do we represent quantum states, how do we represent quantum transformations of those states in Ket and matrix forms, and then we also looked at the circuital model of quantum computing. We broke down our quantum information processing task into a sequence of elementary gates. We also saw how do we implement those gates, not physically but mathematically. This was the first part of our course. We also in the process looked at some paradoxes related to measurement. We also introduced entangled states, defined entangled states, and so on. So the first 1/4 of this course has been devoted to fundamentals. The second major thing that we've undertook is looked at various kinds of quantum algorithms. And through these algorithms, we have some sense of how quantum information processing tasks unfold on a quantum computer. And as you do your projects, which we're going to announce a submission date for those projects, you'll probe deeper into quantum algorithms, analyze the performance of quantum algorithms, draw circuits that implement algorithms, simulate those algorithms, and possibly test them out on a real quantum computer as well. So this is what we've done so far. Now, the remainder of this course will also have 2 components. The first component that I'm going to start today is looking at the nature of quantum information. And in the process, I will also describe 2 important applications. One is of quantum communications and cryptography, and the other is of quantum error correction. And I hope we do get time at the end to look at our 4th major idea in this course, and that is exemplifying the quantum information processing task through some implementations. And by the way, you've already seen one kind of implementation, and that was through single photon hardware realizations in Bilal's talk. So today we're going to start our discussion on the nature of quantum information. And precisely we're going to build up our understanding of how we quantify information, what is entropy, how do we measure information, how do we look at the fidelity of communication between 2 parties, Alice and Bob, how can we do eavesdropping free, perfectly secure quantum communication, which might transform the way in which human civilization operates and exchanges information, and we'll possibly look at quantum error correction too, because we would like to make our quantum computers fault tolerant. So any questions about the overall scheme of this course so far? Alright, so first of all, I would like to discuss the idea of some basics, some preliminaries before we get into the nature of quantum information. Luckily, all of you have taken a course on probability, so we're going to use some concepts on probability as well. We're going to use the Bayes theorem, we're going to use conditional probabilities, and so on. You've already taken a course on thermodynamics as well, which means you know what entropy is. So all of this is now going to come together. But for the time being, for today, I would like to focus on this concept of a density matrix or a density operator. So suppose I have a quantum state psi. Now this is a ket. This lives in a Hilbert space. It could be capital N dimensional. So if you have small n qubits, the dimensions are 2 raised to power n. So it becomes a capital N length column vector. So this is a quantum state. But this is a special kind of quantum state, and that's not the only kind of quantum state that exists. This is a state that is called a pure state. Alright? Now you've also come up with the idea of a projection operator in your quantum mechanics courses. Now projection operator is of course an operator, so it must be a matrix, and is given by, so the projection operator is given by the ket psi followed by the bra psi. Alright, so this is the simplest example of a projection operator. So let's call this the projection operator on the state psi. So this operator acts on another quantum state, on another pure quantum state. For example, if this projection operator is made to act on another quantum state phi, let's see what the output is going to look like. The output is going to look like ket psi, bra psi acting on the state phi. Right, so here is our initial projection operator. Now this acts on the state phi. Now this is the beauty of Dirac notation, that the kets and bras, when they come together, they give rise to new objects. So this new object is formed. This new object of course is an inner product between ket phi and ket psi. So it's an overlap between two states, and this must be a complex number. It's some kind of probability amplitude. So this is the projection of the state phi on to the axis psi, isn't it? So this gives rise to some complex number C. I can just put C phi psi just to, for labeling purposes, and the quantum state psi. So what this projector does is that it takes an arbitrary input and projects it parallel to ket psi. That's why this is called a projection operator. If initially ket phi is orthogonal to ket psi, this is 0, so the projection operator will yield nothing, will yield vacuum, nothing. If phi and psi are parallel, so they are the same state. Since both of them are normalized, so phi equals psi, so at the same state, nothing happens. Then phi is an eigenstate of the projection operator. Right, so this is the idea of a projection operator. Right? So, okay. So another concept that is really important. So if I were to take an operator, which is the projection operator, how do we one way of defining the projection operator is that if I operate twice with the projection operator. Remember that in this is simply what is generally called the measurement postulate. That is, you're measuring something, you're creating a new state. The new state that you're creating is psi. So measurement is also, strong measurements are also implemented by projection operators. So when you have a detector, you're projecting on to ket 0 or ket 1. So another definition of a projection operator is that if it were to be implemented twice in succession, so once followed by another instance, then this object here, since the state is normalized, this is just 1, and you're left with ket psi, bra psi, which is the projection operator itself. So once you've created, so adding the projection operator in concatenation one after the other means that you're creating a new state, then you're projecting onto the same state again and again and again and again. So adding the projection operators one after the other is as good as adding it once. Alright? So this is a property of projection operators. You can add the projection operators any number of times and it yields the same operator. Alright. Now if I were to take the projection operator on the state psi and sandwich it between another state, which means I form this inner product. Let's see what happens. So isn't this called the expectation value of this operator in the state phi? That's what this thing is called. So you take any operator here and sandwich it between the state. This will give me the expected value of that operator. So if I were to measure that operator and the state that I'm measuring it upon is phi, what is the average outcome that I get? That's what the expectation value means. Basic quantum mechanics. So are you familiar, brother, are you familiar with this kind of? All right. So let me finish this and I'll backtrack a little bit. So if I input a state phi and I measure it, this is something that you've already seen in the course. So now in what basis am I measuring it? Suppose I measure it in a basis ket 0 or ket phi, which really means that since I'm dealing with qubits, my state can be alpha ket 0 plus beta ket 1. Now suppose before this, so this is my input state and this is my detector. And before I make this quantum state fall onto the detector, I have a device. Certain device. Now that device every device has an operator description. Suppose this device has an operator description ket psi bra psi. Right? So this operator must be a matrix. This is indeed a matrix. A ket followed by bra, which is what we call as an outer product, is a matrix. Now what this does, a new state is created here. So this operator acts on this state phi, and this is the new state that emerges over here. Now this must be some complex number. Some complex number. Let's call it C. So this is some complex number C. It's a scalar. Followed by this state psi. So a new state has been created here, which is proportional to ket psi, which is the state from which this projector is built. So this projector is projecting onto the state psi. Suppose this operator were ket 0, bra 0. When this operator acts on phi, let's see what the output is. Now phi is given by this. Its inner product with ket 0 is alpha. Alpha ket 0. So a new state has been created, which is alpha ket 0. By the way, since we always like our states to be normalized, this alpha is not necessarily equal to 1. So the new state that we are creating is really this, get 0. So this becomes like a global phase. But it's important for probabilistic measurements. Anyway, if our so what the projection operator does is that it creates a new state, get 0, which is parallel to its own axis. Now if you do optics, so you have a polarizer. What a polarizer does, it passes the electric field that is parallel to its axis. That's an example of a projection operator. Alright, so now if I were to put this projection operator inside a cat and a bra, this thing is called the expected value of this operator. So let me do a little bit of quantum mechanics here. So for this you probably need to get back to my quantum mechanics lecture. So I have a state psi, and this is just a cartoonic representation. I'm measuring something. Since I'm measuring something, associated with that measurement, there is some operator. Right? That operator is also called an observable. Suppose I'm measuring an observable A. Right? So I input a quantum state and I'm measuring, for example, if I were to measure I could measure its energy, right? Then this observable is called a Hamiltonian. I could measure its polarization, or if I'm talking about a photon. Alright, so this is some observable. It could be a momentum operator if I'm looking at the momentum. It could be the position operator if I'm measuring the position of this object. And different outcomes are possible. So when I've done a measurement, different outcomes are possible. Now, the act of measurement collapses the quantum state. And now I have some meter that is showing me outcomes. So I'm getting classical measurements. And the measurements that I am getting are real numbers, which are measurement outcomes. Right? So those real numbers are A1, A2, A3, A4, and all the way up to AM. So these are real numbers. Suppose I'm measuring the position of an electron. So my quantum state is the position of an electron. Right? And I'm measuring it with a position operator. Then my possible outcomes are the positions of the electrons in nanometers, 1 nanometer, 1.5 nanometer. In fact, since the position operator is continuous, the outcomes are also continuous, but I can also have discrete measurements. For example, if I were to measure the polarization, I know that it suffices to measure the polarization along a horizontal or vertical. Then I have two possible outcomes. Am I getting a horizontal output or am I getting a vertical output? Right? So I can have a discrete operator or a continuous variable operator. But let's focus our attention on discrete outcomes. So all of these outcomes yield numbers, real numbers, because after all, measurement outcomes must be real numbers. The complex numbers are hidden within the quantum state. So these real numbers, suppose all of them are different, distinct. Let's suppose that. These real numbers are in fact, how are they related to capital A? How are they related, or they're not related at all? These are the eigenvalues of A. So if I take the matrix form of A and I were to find its eigenvalues, those eigenvalues will be A1, A2, A3, and so on. N distinct eigenvalues. Alright? And the probability that I get AI as an output, what's this probability? If my input state is ket psi, this thing, but we're not talking about projection operator. This is a general kind of operator, A, capital A. So what we need to do, we need to construct the projection operators. So associated with each eigenvalue, there is an eigenvector. So associated with this eigenvalue, there is an eigenvector. Let's call that eigenvector ket A1. Let's call this eigenvector ket A2, ket A3, ket A4, up to ket AN. So this probability is going to be the inner product of the input state upon which the measurement is taking place with the eigenvector associated with this eigenvalue, modulus square, right? This is how quantum mechanics works. This is how a strong measurement in quantum mechanics works. This is the probability that you're getting AI as an outcome. That's your outcome. And of course, this is the input quantum state and its projection on the associated eigenvector modulus squared. Now, this thing can also be written in this fashion. Right? So you take this complex number and write its complex conjugate. Correct? Now if I look at what's sandwiched in between, this is a kind of a projection operator. So this thing becomes the projection operator. Let's note that by capital P. This P without a hat is a probability. This is a projection operator onto AI. Okay? So the projection operator sandwiched between the input quantum state. And this thing is called, this object is called the expectation value of this operator. And you denote it by this fashion, in this fashion, expectation value when the state is psi. In general, the expectation value of an operator in the state psi is given by A sandwiched between psi. So this is our definition of the expectation value. All right. So this is the probability that we get AI. So the probability of getting a certain eigenvalue is the expectation value of the projector operator. I can write this down. The probability of getting some eigenvalue is the expected value or the expectation value of a projection operator. remember also that if I were to take the expectation value of an arbitrary operator, what will that look like? So suppose my psi is given by, since those eigenvectors a1 to an span the entire Hilbert space, the Hilbert space can totally be described, any quantum state in that Hilbert space can totally be described in terms of those eigenvectors. They form an orthonormal basis, because we are also assuming that everything is non-degenerate, all the eigenvalues are unique. Then any psi can be written as a sum of all of these eigenstates with some complex amplitudes, right? Correct? And any operator A, if it corresponds to a measurement, then it must be an observable, which means its eigenvalues must be real, which means that if the eigenvalues are ai, then this operator can be, when you write an operator in its eigenbasis, it's diagonal. And the diagonal means that the values in the diagonal are just the eigenvalues, and the diagonal matrices has elements, for example, A1, A2, A3, all the way up to AN, and zeros everywhere else. Now, if I have zeros everywhere and A1 at the top level, then this really means, since this is an eigenvalue A1, this matrix with 1 here and 0 elsewhere would really mean let's put this, ket A1 bra A1 plus, now this with the 1 here, I would get A2, ket A2 bra A2, and so on, right? This is my operator A. My operator A therefore is AI, ket AI, bra AI, sum over all the I. So this is my operator A. This is my state psi. Now if I were to formulate this expectation value, what will the result look like? So my outcomes are the eigenvalues, but each eigenvalue is going to be weighted by a probability, and that probability has something to do with this. So if I were to form this expectation value, let's give this as a homework, Abdullah. So this really means my operator A is being sandwiched between psi in this fashion, and my operator A is really this. Right? My ket psi is really, now I'm going to change the indices, J, Cj, ket J. Right? I want to change the indices, right? And for the bra, I also want to change the indices again. Ijk, Ck, star, bra K, right? Big sigma with an I, with a J, with a K, Ck star, Cj, AI, bra K, ket AI, bra AI, सॉरी इसको ए जे कर दें, ए आई ए के right? Now these are inner products and we are assuming non-degeneracy here. All the eigenvalues are different, so the corresponding eigenstates are orthogonal because the eigenvalues are distinct. This is called non-degeneracy. So in this case, this is non-zero only when I equals j. And when I equals k, so k must be equal to j. So when k equals j, this j summation sign goes away. This becomes ck star ck, right? So I'm left with I and k, ck star but I must also be equal to k, right? Because I equals j and I equals k, so I must also be equal to k. So I can put an ak here as well, and I can just get rid of this summation I. Got it? So this is the sum of eigenvalues, but each eigenvalue is weighted by a probability term ck mod square. This is the expectation value of this operator. So the expectation value of the operator are all the eigenvalues, but each eigenvalue has to be weighted by a probability term. So that's how you find the expected value of any variable. You take the value of that variable and multiply it with the corresponding probability or frequency of occurrence of that outcome. So this is an outcome and this is the frequency of occurrence of that outcome. So now what we've done, we've looked at a projection operator, we've had some clue of what the expectation value of a projection operator means. The expectation value of a projection operator gives us really the probability that that outcome is obtained here. And we also now know what is meant by the expectation value of an operator. The expectation value of an operator is the weighted sum of the eigenvalues of that operator. So let me give you one example that all of this makes sense. So this is basic quantum mechanics. This is mostly done for you, but do look up some of my lectures or some other tutorials on this subject. Suppose I have a quantum state psi and I'm talking about the polarization of a photon. Let's talk about a polarizing beam splitter that has two channels, ket 0 and ket 1. And then I put two detectors here. Now this entire measurement scheme can be represented by an operator. So what I'm doing is I am sifting or differentiating between ket 0 and ket 1. I am projecting onto ket 0 or ket 1. So what I would like to do, I would like to write a measurement operator for this scheme. A suitable measurement operator could be ket 0 bra 0 minus ket 1 bra 1. That's a suitable measurement operator. And if you notice, this is a sigma z gate. So now so if I were to write this in matrix form, and I will use the ordering that I'm used to, this will be a 1 here, 0 minus 1. Of course, this is written in its diagonal form. One eigenvalue is plus 1 and the other eigenvalue is minus 1. So if I were to take the eigenstructure of this matrix, it's evident because it's already diagonal. If it were not diagonal, I could diagonalize it. Since this is a Hermitian operator, it's an observable, I can always diagonalize it. The eigenvalues are +1 and -1. So there is really a +1 here and a -1 here. Right? So this operator A, remember, can be written in this form. So one eigenvalue is +1 with ket 0, bra 0. The other eigenvalue is -1 with ket 1, bra 1. Alright, and the if my input state, say psi, were simply ket 0, say, let's say, this was my input state, then the probability that I obtain ket 0 as my output has to be 1, right? Let's see if it makes sense. So this is my state. So what I want to do, I want to form the projection operator associated with the outcome. That projection operator is ket 0, bra 0. So this is my projection operator, and I want to find its expectation value when the state is psi. Right? So this thing is the same as this thing here. This of course is psi is 0 anyway, so this is 1. If my input state were C0 ket 0 plus C1 ket 1, the probability of obtaining ket 0 would be projection operator associated with the outcome that I'm measuring is ket 0. So the projection operator associated with this is this particular thing, this projection operator. The state is psi C0 ket 0 plus C1 ket 1 and associated bra C0 star bra 0 plus C1 star bra 1. Now simple algebra. This term survives, this term goes away, so I'm left with C0, right? And here, this term survives, so I'm left with C0 mod square, as it should be. Correct? And if I were to have this input state, what is the expected value of this operator? What's the expected value of this operator here? Say 0? No. No. Follow?
C0 mod square minus C1.
Exactly. C0 mod square minus C1 mod square, which is really C0 mod square times the associated eigenvalue plus C1 mod square times the other eigenvalue. So this is the expected outcome. So if I were to repeat this experiment a large number of times on identical copies of ket psi, and I would look at all my outcomes and find the average, this will be the average. It's going to be some number, 0.1, 0.3, 0.5, 0.6. That's the expected value of this operator. So in a measurement scheme which is measuring this observable A, the outcomes are all, every time I get a single eigenvalue, either 1 or minus 1, 1, minus 1. So I will get some sequence of 1s, minus 1, right? And if I were to find out the histogram or the frequency of occurrence of +1, that would be C naught square and conversely, right? And the average of these will be C naught square minus C1 mod square. And if of course I were to input 1 over under root 2 get 0 plus 1 over under root 2 get 1, then my expected value will be 0. But remember, the last thing, there is always some spread in the outcomes as well. Right? So, these are my outcomes. So the outcomes will look like this. This is basic quantum mechanics, and if you want to do quantum information, we need to know all of this. So if I were to do this experiment, then in some run of the experiment I will get some outcome, in another run of the experiment I will get another outcome, and so on. Right now I am talking about large dimensional input, quantum inputs, not qubits. So I get spread of outcomes when I'm measuring A. The average of these outcomes, this thing is right? That's the average outcome. And there is also a spread. Let's call that spread delta A. In quantum mechanics, this is also called the uncertainty in A, in your measurement outcome. And basic quantum mechanics tells us what this uncertainty is. So can you identify what the uncertainty is going to be? Basic quantum mechanics 1. So the square of this is A squared expectation value minus, right? This is called the uncertainty in A. So with this primer, let's move on. Let's move on to density matrices. So this is a quick primer of measurement in quantum mechanics. In its simplest form, strong measurements, projective measurements as they are called. There are other kind of neat ways of measurement as well, weak measurements and so on, but we're not going into that domain as yet. So now I would like to talk about density matrices. Psi, ket psi is just one kind of a state, right? Now let me, in order to bring out the intuition in a clear fashion, if I were, let's talk about a single qubit. I've written a state for a single qubit, an arbitrary state for a single qubit. C0 and C1 are complex numbers. It's a normalized state. C0 mod square plus C1 mod square must be equal to 1. Is this a pure quantum state? Now, if I were to, can I write this as ket psi? Yes, I can. If I were to take this state psi and so if I were to take this ket psi and add to it the projection operator, add to it the bra, so that I make this into a projection operator. So now I have a quantum state, and I have mathematically made a projector out of it, which means that I can have any input state and I'm projecting onto this state. So if this state were to act on another state, the output is going to be proportional to ket psi. So this way of writing the same state, I've done nothing. I've just taken the ket and put it together with the bra. Now this becomes an operator, but it also is another legitimate way of writing the state. This thing will get clearer as we look at an counter example. So this manner of writing a state is given a symbol rho. You put a hat on top of it if you desire so, because it's an operator. And now it's a matrix that represents a state. Normally, if you're looking at quantum mechanics for the first time, in your first course, you don't have to do this because all your states are represented by kets. But in reality, in real applications, in real implementations, a ket doesn't survive. A ket is extremely fragile. It interacts with the environment and decoheres, and you're no longer left with a ket. You're left with something messier. So we need to have a more general description of quantum states. So let me give you an example. So this is the first step of motivating density operators or density matrices. Another step. Suppose I have a box, a hypothetical box, and I have, just don't take me too literally, I'm just trying to give a motivation. I made a really big box, so that's going to take a lot of time. So I have a box, and inside that box I put in qubits, physical objects, and I'm looking at some degree of freedom, so I'm describing them by qubits, and all of them are identical. So I'm putting identical qubits in here, or identical particles in all of them in the same quantum state. That's what I mean by identicality. Identical particles, all of them in the same quantum state. Suppose that quantum state is psi. So I put one particle state psi, another particle state psi, another particle state psi. Someone has put this ensemble of particles into this box. All of them are identical, same state. Somehow nature has given me these particles. For example, photons coming out from a monochromatic laser. All photons are in the same state. Or a Bose-Einstein condensate. Somehow I've gotten these identical particles. Now it's unless you have certain cunning schemes, it's impossible to measure a quantum state psi. What at best you can do is find probabilities. So quantum mechanics in its traditional form gives you outcomes and the statistics of outcomes. All of that what we've seen are statistics of outcomes. Now if this box were a black box, and some party had prepared that black box and given it to me, the party who was preparing, the chef of this recipe, knew that all of these particles were identical, and then he put all of these particles in a box, sealed the box, and gave it to Manur. Now Manur has this box, it's a sealed box. She doesn't know what's in it. So if she were to take out a particle, now probabilities can be a priori, which means that a probability tells you, an a priori probability means that you need to predict what the outcome is if you were to make a measurement. Suppose all of these are qubits. The probability that output ket 0 is measured. So Manur measures, she does an experiment of that kind, puts it in a beam splitter that can separate out between ket 0 and ket 1, applies that projection operator, which is called, by the way, a polarization operator or a sigma z operator, and she were to measure her outcome, she will get ket 0 with some probability, say C0 mod square, between 0 and 1. And she will get some probability of ket 1, which is C1 mod square. right? Suppose each of these cats psi were given by cat 0, 3 over 4 under root plus 1 over 4 cat 1. This is, the chef didn't reveal this secret, who had prepared the box. He didn't reveal it to Mahmood, but that's what he really did. So if Mahmood picked out one particular particle from the box, of course she cannot tell what the probabilities are, because probabilities really mean that she has to do an experiment on a large number of particles to ascertain what the probabilities are. In one go she will either get cat 0 or cat 1, right? But if she were to take out all the balls one by one and did a measurement and plotted her results, sometimes she would get cat 0 and sometimes she would get cat 1, and cat 0 will appear this number of times and cat 1 will appear this number of times, right? And this height, the normalized height, would be C naught mod square, the normalized height, right? And this height here would be C1 mod square. Now, all of these particles are in a pure state. Each particle is in a pure state. If she were to take out just one particle, and she is only allowed to take out one particle, she is forbidden from taking out a second particle, then there has to be some a priori probability that her outcome is cat 0, and that a priori probability will be C mod square. And the a priori probability that her outcome is cat 1 will be C1 mod square. She will never be able to tell for sure whether these are her outcomes, but if one were to step back, the probability that cat 0 appears will be proportional to this, and this probability will be proportional to this. Now let's take another scenario, and that scenario means that so if this state were prepared, let's give discrete values here. This thing is going to be 3 by 4 and this thing will be 1 by 4. So she will get this outcome with 75% probability and this outcome with 25% probability. But in one go, she wouldn't be able to tell what the state is, by the way. Now suppose there's another preparation. So this is a state preparation scheme. If there's another preparation which looks like the following. It has a number of particles, but 75% of those particles are in the state cat 0 and 25% of the particles are in the state cat 1. Now there is a mixture of quantum states. This is not a mixture of quantum states. These are all identical states. A mixture really means that two non or dissimilar states are mixed together. This is really an ensemble of identical quantum states, correct? And each quantum state is described by superposition. This is not a mixture of cat 0 and cat 1. It's a coherent superposition, right? It's a coherent superposition. Now let's look at an alternative scenario. In this alternative scenario, there are two kinds of quantum states, particles that have been put into the box. 75% of them are ket 0 and 25% are ket 1. So I just draw the, first of all I draw the ket 0. So these are my ket 0 states. And I draw 25% of the balls are in ket 1 particles. Now the preparer of the state puts in these two kinds of quantum states into the box, seals it up and gives it to Manu. Now at random she just juggles everything together so that everything is mixed up together really nicely, and she picks out one particle from this. Now quantum mechanics tells you, at best it can give you statistics of possible outcomes. Now what is the a priori probability that she detects ket 0? Now if I were to make a frequency histogram and I would like to plot the probabilities, again there are two possible outcomes, ket 0 and ket 1. So what's the chance that she's going to pick out a ket 0? So she subjects her particle to the same kind of measurement scheme as we have over there. So what's the probability that her outcome is ket 0? Sorry? Ket 0 की probability 3/4, right? Exactly the same. Exactly the same here. 1/4 and 3/4 here. So by looking at these outcomes, she is not able to distinguish between these two scenarios. And these two scenarios are clearly different. They're clearly different. Right? So what we really need is some kind of mechanism to distinguish between these states. Now a particle picked up at random, every particle must be describable. Any one single particle must be describable by some measure, by some operator or state. It has to be given a mathematical form. Now if in this case you cannot associate, so if I were just to take one particle out of it, what would be the state of that particle? So my question is, two questions. This scenario, step back, you're some supernatural being who can see what's inside the box. So if I take out one particle, and I ask you, what's the state of that particle? You can associate it a state with it. It's psi. It's 3/4 under root ket 0 plus 1/4 under root ket 1. Now in this scenario, if I were to take out a particle, still it hasn't been measured, but quantum mechanics must, a state gives you the potentiality of outcomes, right? The state gives you the possibility of an outcome, the potentiality of an outcome. What are the possible outcomes? What is a quantum state? A quantum state tells you a priori, beforehand, what are the statistics of the outcomes. So what is the quantum state in this scenario? It can't be this. This is not this state here. It's not this state here. It's not prepared as a superposition. So we need to have another description of this state. In fact, it cannot be represented by any ket whatsoever. Right? You can't do that. So in both of these cases, we have one consistent mechanism of writing quantum states. Suppose I have an incoherent mixture of states. Psi k I have a state, pure quantum state psi, incoherent mixture of pure states. So I take pure states and mix them together. So I take the state psi k, and the amount of psi k or the fraction of psi k in that mixture, suppose that's wk, w for weight, with wk is between 0 and 1. For example, I have state psi 1 and the amount of psi 1 in fractional terms is w1. I have psi 2 and the amount of psi 2 is w2. And I mix up to n kinds of quantum states, wn. Now each of these states is normalized. Correct? And these w's are such that I take the sum of all these w's must be equal to 1. So I have 30% here, I have 30% here, I should have 40% here if I have 3 kinds of states mixed in. So all of these w's, the sum of these weights must be 1. Each weight of course must be between 0 and 1. Right? So if I have this kind of incoherent mixture, each quantum state, by the way, can be a pure coherent superposition. Each of these could be a superposition. So if I were to take psi k and take the ket and put it together with the bra and weight this by wk and sum over all the k's from 1 to n in this example. Now n is not the number of qubits, by the way, so don't confuse this with the number of qubits. This is just the number of kind of ingredients inside the mixture. This thing is called the density operator. Okay? Remember, each of these states, this state on its own is normalized. Otherwise, nothing is going to make sense. Examples. So in the first example here, let's look at this example. There is only one kind of quantum state inside the mixture. Only one kind, because all of these particles are identical. Only one kind. So rho will be, and so there's one kind, so there's only one W, which is 100%. And psi, of course, is 3 by 4 ket 0 plus 1 by 4 ket 1. This is the ket, and the corresponding bra is right, and W is just 1, so the summation just has one entry in it. Right? So if I were to write this out, this becomes 3 by 4 ket 0 bra 0 plus under root 3 by 16 ket 0 bra 1. Remember, this is an outer product plus 3 by 16 under root ket 1 bra 0 plus 1 by 16 under root I can write this in matrix form as well. In my basis, choice of basis is ket 0 followed by ket 1. In matrix form, this will become इसको 9/16 लिख लेता हूँ, जरा आसानी हो जाएगी। So this is the density operator associated with that pure quantum state. So if I were to take out any particle from this, that particle will be completely describable by this operator. So it's not of much use for pure quantum states because it's equally describable by just this ket. So for pure quantum states, the ket is an easier prescription to work with because a pure quantum state is describable by a ket. Correct? So it doesn't, but the definition holds true even for pure quantum states. Alright? Now if you look at this matrix here, certain things you will notice. The first thing you notice, if I were to take the trace of this matrix, what's the trace of this matrix? 1. Trace is the sum of diagonal elements. So density operator has certain properties. यार फोन छोड़ दो भाई, कोई बात नहीं, 2 मिनट रहेंगे. So the trace of this matrix is 1, right? And is it also Hermitian? Yes, it's Hermitian. The diagonal elements are always real. The off diagonal elements can be real or imaginary, but it's always Hermitian. So, and if I were to take the eigenvalues of this matrix, a Hermitian matrix has real eigenvalues. So this is the density operator for this scenario over here. Now let's look at the density operator. If I were to take out a single particle from the second scenario, what will be its state? Its state is not describable by a ket because we now have an incoherent picture. So we need to have a prescription that describes the quantum state of that single particle that has been drawn from the box. And from that prescription we want to find out if all the statistical outcomes hold true. So for the second scenario, the bottom scenario, we have two kinds of states that are mixed in. One is ket 0, right? So ket 0, bra 0. And what is the fraction, the weight of this state? 3/4 without the square root, right? Plus 1/4 this is the density operator for the second scenario. And if I were to put this in matrix form, 3/4, 0, 0, 1/4. Trace is again 1, it's Hermitian. Eigenvalues are evidently 3/4 and 1/4. So there are three properties. Its trace is 1. Because if the trace is 1, because the sum of these weights is 1. Right? Here the trace is also 1. And somehow these objects are 0, but they can be non-zero as well. So density operator has trace always 1 because otherwise the state is not going to be normalized, and the density operator is also Hermitian, which implies that the eigenvalues are real. Now one thing I would like to end of this lecture with is, if I were to take rho, by looking at rho, how can I tell whether it's a pure state? This kind of state in which there are more than one non-zero weights, it's called the Schmidt number, which there are more than one non-zero weights, is called a mixed quantum state, as opposed to a pure quantum state. A pure quantum state can always be written as a ket. Now how can I tell by looking at the state rho that a state is mixed or pure? Huh? Sorry? No, but okay, let's see if that off-diagonal argument is correct. Suppose here you have off-diagonal elements, right? So this is pure. What if I have mixture of what if I prepare this matrix, this state? Now this is a mixture of two kinds of two pure states, so it's not pure, right? It's not pure, but still it's a density matrix because this is a pure quantum state. I find the outer product, so and I look at this weight 3 by 4. This is another pure state, but I'm mixing these pure states in a ratio of 75% to 25%, and if I were to form the density matrix for this, this will also have off-diagonal states, off-diagonal terms, right? So looking at the off-diagonal terms doesn't tell you that the state is pure or mixed. If there are,
if off-diagonals are at 0 more, then it will not be pure.
no, off-diagonal 0. For example, if you have this state, get 0, pure state. Its off-diagonal terms are still 0.
But when it is a condition like I K W K
So कहने का मतलब है कि off-diagonal terms don't tell you anything whether a state is pure or mixed, right? By the way, the off-diagonal terms are also called coherences, and these terms are called populations as well. So how can you check whether a state is pure or mixed? You can check that by a simple mechanism. If I have rho, what's the trace of rho for pure or mixed? 1. For both of these cases it's 1. Right? Now for a pure quantum state, we know that rho is equal to some ket. Right? Some ket. So this is how we define a pure quantum state, right? If I were to take the trace of this, of rho, of this rho, right? Now the trace of an outer product, this outer product, the trace is always a scalar. So this is equal to bra d ket A. Remember this. How do you know this? Because the trace of anything, say any x, is, how do you define this? This is, right? So this is how we define the trace of an operator, you take the diagonal elements of the operator. The diagonal elements of the operator are represented by this form, right? So you take the trace of this operator. This is how you define the trace of an operator. So if I have trace of ket A bra B, this is an operator. This is going to be I A B I ket I. Now this is non-zero when A equals I, and this is non-zero when B equals I. Correct? Now A must equal I and B must equal I. This really means that this should be true, right? Which really means, now what is this? This is inner product of A with B. Correct? So if you have an outer product and you want to find the trace of this, you just change the order of the ket and the bra, you will find the trace. Now if you look at this thing, the trace of this thing, of this pure, the density matrix corresponding to a pure quantum state, what is this going to be equal to? 1. Because this is the inner product of psi with itself. Psi by definition is normalized. We always deal with normalized quantum states, otherwise we just blow out of the window. I mean, nothing is going to work. Now if I were to take, now this is only true for, is this only true for a pure quantum state? If I were to take Wk and find a trace of this, right, for a mixed state where K is where K is greater than 1, right, some n, right. This is the general form of a density operator. So this becomes K, Wk, this is a scalar. Now trace, this is a number, so trace goes inside and acts on the operator, because you might find the trace of an operator. This is just being multiplied by a number. Trace of psi k, right? But this is again equal to 1. So we left with, right? But this is also equal to 1. So both pure and mixed quantum states, when they are written in density matrix form, they have a trace equal to 1. So you can't look at the trace and tell whether rho is pure or mixed. Any other thing that you can think of to try to do?
Rho square.
Shabash. So if we were to take rho square and take the trace of this for a pure state, this is still going to be 0. Because rho square for a pure state, the density matrix of a pure state is actually a projection operator. So this is 1 second, right? This is again equal to rho, only for a pure quantum state. This doesn't hold true for a mixed state. So if trace of rho square equals 1, it's called a pure state. If trace of rho square is less than 1, it's a mixed quantum state. Alright? If you have a block sphere and I'm talking about a single qubit, pure states live on the surface of the block sphere. Mixed states live inside. And there's one extreme is pure state, the other extreme is a maximally mixed state. I'll explain that in the next lecture. So this is just a motivation for density operators. We'll look more at density operators. In the next lecture, we're going to look at different kinds, how to quantify information, what is Shannon's entropy, and so on. So inshallah, in a day